So let us begin with an immediate property that a ring homomorphism has. That is, suppose you take this can be treated as a lemma. Suppose you take a ring homomorphism phi from R to R dash. Okay. R dash be a ring homomorphism. Then you will have the following two immediate property, that is, one is phi of 0 goes to the 0 of R dash, and secondly phi of minus x equal to minus of phi x for all x belongs to R. So these are immediate, because suppose you take phi 0, so then phi 0 can be rewritten as phi 0 plus 0, that is phi 0 plus phi 0, and from which you can cancel out this phi 0 from both sides, and you will have phi 0 equal to 0. Okay. Secondly, this is one. Number two, suppose you take phi x and add it to phi of minus x, then it will be phi of x plus minus x. So that is going to be 0, and phi 0 is 0 from 1. Similarly, phi of minus x plus phi x is 0. So this proves that the negation of phi x is phi of minus x. Okay. Now one may be tempted to prove that, suppose you have suppose you consider R and R dash a ring with unity. Suppose R dash are rings with unity 1R, 1R dash respectively. Okay. Now one may be tempted to prove that phi of 1R is equal to 1R dash. But this doesn't hold in general. This is not true. But if you impose some condition on R dash, or if you can impose a condition on the map phi, then we will see that this will happen. Okay. So this will be happen to be true. Now what are the conditions that you can impose on R dash and phi? So suppose you take firstly case 1, R dash the integral domain. Now why we consider this condition, because if you take phi of 1r, then it will be phi of 1r dot 1r, right? Then it is phi of 1r dot phi of 1r, as phi is a ring homomorphism. So that means it is phi of 1r minus phi of 1r dot phi of 1r. So this is going to be 0. So that means phi of 1r dot 1r dashed minus phi of 1r. This is 0. So therefore the product of two elements in r dashed is 0. Now to make this one 0, we need to assume that r dashed should be an integral, right? So if r dashed is integral domain, then now since r dashed be an integral domain and it is true that phi of 1r not equal to 0. Why? Why it is true? Because if phi of 1r is 0, then what will happen? Then what will happen? Then phi of x is phi of x dot 1r, so it means it is phi x dot phi of 1r, so that is it is 0, and this is true for all x belongs to R. So that means phi is the 0 function. Okay, so the only possibility is that phi is the 0 function, provided, so we take that provided phi is non-zero. Okay, so then you can say that phi of 1r is not equal to 0. Then so since r dash to be an integral domain and phi of 1r not equal to 0, so 1 r dash minus phi of 1r, it must be 0. So that is phi of 1r is equal to 1 r dash. Okay. Now case 2. Now if we assume that r dash be arbitrary, you do not need to take r dash to be an integral domain. It is an arbitrary ring, and you are going to impose a condition on the map phi by taking it to be onto, that phi is onto. Okay, then you will see that phi of 1r equal to 1 at dash. Why? Why it is true? Because for 1 r dashed, so it is a member of r dashed, so there must exist one x belongs to R such that the image of x under phi is going to be 1 r dashed, right? Okay, so this means So phi of 1r dot x, this is 1r dashed, so this is phi of 1r dot phi of x, this is 1r dashed, but you have already assumed that phi of x is 1r dashed, so you just putting 1r dashed in place of phi x, so this is true, so that means phi of 1r equal to 1r dashed, so this is the case. Okay, so if you assume that either r dash be an integral domain, or if r dash be arbitrary, then you need to impose a one condition on phi which needs to be on 2, then you will see that 1r goes to 1r dashed under the ring homomorphism phi. Okay, so this is a very nice kind of observation of a ring homomorphism, from a ring with unity to a ring with unity. Now we are attempting to define kernel, which is much analogous to the definition of kernel of a group homomorphism that we have already studied in our group theory course, right? So kernel of a homomorphism, ring homomorphism. So what does it mean? So a ring homomorphism, basically it is firstly a group homomorphism, right? So if you suppose that phi be a ring homomorphism, so in view of its first condition, that phi of a plus b needs to be equal to phi a plus phi b, and r plus and r dash plus both are abelian groups, so therefore phi is eventually be a group homomorphism under the group homomorphism of the additive groups r plus and r dash plus. Okay, so in an analogous way you can define kernel of a ring homomorphism in this way, that is, so we define kernel of phi, or we can denote it by ker phi or simply k phi, which is defined to be the set of all x belongs to the ring R, which will be mapped to the 0 of r dashed via the map phi. Okay, so this is the definition of the kernel of a ring homomorphism, which is same, which is the kernel of the group homomorphism phi. Okay, in between the additive groups r plus and r dash plus. Okay, fine. So as we have already proved in group theory course that kernel of a group homomorphism will be a normal subgroup of the domain group, right? So in a same sense we can prove that here that kernel of a ring homomorphism will firstly be a subring of the ring R. Okay, so let x y belongs to k phi. Okay, then what would be the image of phi x minus y? So it is phi x minus phi y, but both are 0. 0 minus 0 is 0. So therefore x minus y is again in k phi, which proves that k phi is a subring of R. Okay, why? Because phi of xy is phi x phi y, and this is again 0, so xy belongs to k phi again. Okay, so therefore this is a subring of R. But apart from these two properties, this k phi has another important property, that is if you take any element from the ring, and if you take any or all x belongs to k phi, you will see that phi of xr is phi x phi r. Now since x is in k phi, so phi x is 0, so 0 dot phi r is 0. So this means xr belongs to k phi, right? And again similarly you can prove that phi of rx is also 0, and so rx belongs to k phi. So if you take any element from the ring and if you take any element from the kernel, you will see that, so this implies for all r belongs to capital R, for all x belongs to k phi, you will have xr belongs to k phi and rx belongs to k phi. So this is a property which is very important in the theory of rings, and that will be explored in the next discussion. Okay, so these k phi's will be called ideals in R. So this is an ideal in R. Okay, but we will define it in few minutes. Okay, now let us have a look on some examples of ring homomorphism, and after that we can define this ideal, which is very much analog of normal subgroups in a group. Okay, fine. Because you will see that whenever we have already studied in group theory that if you take any normal subgroup of a group, that will be used to construct a new group which is the quotient group of G by the normal subgroup N, right? So in a similar way we will construct a new ring which will be the quotient ring of R by an ideal I. Okay, so that is why it seems to be very much analogous to the concept of normal subgroups in a group. Okay, now let us have a look on some examples, and firstly you can have the example of a ring homomorphism which is phi of x goes to 0 for all x. So this is evidently be a ring homomorphism, and this is called the 0 homomorphism, right? Okay, and again if you take any ring, then the identity map, so phi x equal to x. So this is again a ring homomorphism which is called the identity homomorphism. Okay, and in that case you will see that what is the kernel of phi? So this is a set of all R, all x belongs to R, which will be mapped to 0, but in that case only x will be 0, right? So therefore it is a singleton set, and note that this map is a bijection. This map is 1 1 and on 2, right? So in an analogous way, in group theory, that we have already proved in group theory, that a group homomorphism phi is 1 1 if and only if its kernel is a singleton. In a similar way, you can prove that this can be taken as a theorem that phi colon R to R dashed be a ring homomorphism which is 1 1 if and only if its kernel is going to be singleton. Okay, this will be left as an exercise. এটা প্রমাণ করে দেখো, ঠিক আছে? Okay. Next example. Suppose you take the ring Z root 2, which is, it consists of the elements of this form. Then you can define a map from Z root 2 by this rule. Just check that it will be a ring homomorphism from Z root 2 onto Z root 2. That is, it is a ring epimorphism. And in that case also, kernel of phi is equal to this. So phi is 1 1. Okay. So that means phi is an isomorphism in between these two. This on Z root 2 onto Z root 2. Number 4. Suppose you take the ring Z plus dot and you take the ring Zn. Then you can define a map here. So x goes to x class. So this is evidently be a ring homomorphism from Z onto Zn. But in that case, if you check the kernel, then you will see that this is the set of all x belongs to Z, such that phi x equal to the 0 of Zn, that means 0 class. So that is set of all x belongs to Z, such that x class equal to 0 class. So that means, in view of the relation that has been defined on Z, which will be used to get this ring Zn of residue class of integers modulo n, so this is n divides x minus 0. So that means set of all those x belongs to Z such that x equal to nq, or q belongs to Z. Right? So that means it is a set of all multiples of n. Yeah. So you can denote this by nz. So kernel of phi in that case is nz. Okay. Okay. So now we are going to introduce the idea of an ideal of a ring, which I have already stated that it is very much analogous to the notion of a normal subgroup of a group, and in many situations you may feel that similar kind of results can be obtained between, you can see that the role of an ideal in rings and the role of a normal subgroup in groups are quite same. So because, as I have already told you an example, that you can set up a canonical fashion of construction of quotient groups to construct quotient rings. So to construct a quotient group, you need to have a normal subgroup, and to construct a quotient ring, you need to have an ideal. So this is a very important notion in the theory of rings. Okay. So let us define what does it mean by an ideal in a ring. So suppose you take, so suppose R be a ring, okay, and you take one subset I of R, non-empty subset, okay, then I is called a left ideal or a right ideal or an ideal if number one, as you can see that in the case of a kernel of a ring homosome, we have proved that firstly this kernel is subring. Okay, that means it is enough to state that if you take any xy belongs to K phi, then x minus y is also in K phi. So to prove that K phi is a subring, so it is enough to prove this one. Okay, so our first condition is this: it is for all xy belongs to I, x minus y belongs to I. Okay, and secondly, you can also see in the case of a kernel that this one, that if you take any element from the ring and if you take any element from the kernel, then these two elements also belongs to K phi. So we shall divide these two concepts. That is, firstly we will take this one, which will give us left ideals, and secondly we will take this one, which will give us right ideals, and if both will going to happen, then we call this an ideal. Okay, so firstly the second condition is that for all R belongs to capital R, for all x belongs to capital I is said to be a left ideal if Rx belongs to I, or it is said to be a right ideal if xr belongs to I, or it is said to be an ideal if Rx, xr both are in I. This. Okay. So in this way you can define left ideals, right ideals, and ideals. Now in a commutative ring, you do not need to place two concepts, left ideals, right ideals, separately, because in a commutative ring xr and rx both are same. So in a commutative ring, R, the concept of a left ideal and the concept of right ideals both are same, because xr is going to be equal to rx. Okay, so then we will consider only ideals. We will talk about ideals. Okay, sometimes the ideals that we have defined, it is called two-sided ideal. Okay, some books have mentioned this terminology, two-sided ideals, and we have already have an example of an ideal which is a kernel. So K phi is a kernel of a ring homosome. So this is going to be an ideal, right? So NZ is the complete list of ideals in Z plus dot. Okay. Now number 3, suppose you take a ring and you consider an element x, then you can define two sets. One is x r, which is a set of all elements of this form x small r, where small r belongs to capital R, and another one is r x, that is r x, or r belongs to capital R. So using this x, you can define two sets in capital R. But eventually you will see that the first one will going to be a right ideal. Sorry. And the second one will going to be a left ideal. I just left this to you as an exercise to check that whether these are right ideals and left ideals or not. And if R be commutative, then you see that these two are same, x r equal to r x, right? So that means it is an ideal. Okay. Now one may feel that this x maybe belongs to the subsets, but this is not the case, because x need not be in the given sets x r r x. But if it happens that in a case where you consider a ring to be a ring with unity 1, then you can say that this x will be, so suppose R be a ring with unity 1, then x can be written as x dot 1. So this 1 is a member of R, so therefore it belongs to XR. In a similar way, this x can be written as 1 dot x, so it is in Rx, right? So if you take a ring with unity 1, then you see that x must be in XR and Rx both. And in that case, this XR will be the smallest right ideal. Containing x, and Rx will be the smallest left ideal. Containing x. Okay. So if R will be a commutative ring with unity 1, then these two ideals are same. Okay, then this ideal will be denoted by L angle R angle x. Okay, and it is called the ideal generated by by small x. Now as you see that in this way, in a similar fashion, we can prove that by adopting the similar way of constructing ideals by using elements. You can prove that if suppose S is a subset of R and I will be considered to be the intersection of all right ideals, I or be a right ideal containing S. Okay, so I is considered to be the intersection of all right ideals containing S. So you can check that I will be a right ideal again containing S. And since it is the intersection of all right ideals containing S, so it will be the smallest right ideal, right? Containing S. And in a similar fashion, if you can consider another one, J, which is considered to be the intersection of all left ideals containing S, then it will be the smallest one, smallest left ideal containing S. Okay, and using the same way you can define an ideal, the smallest ideal containing S. Okay, so this I will be denoted by so I will be denoted by L angle R angle S R small r, and J will be denoted by L angle R angle L. And these two ideals are called, this will be called the right ideal generated by S, and this will be called the left ideal generated by S. And if you can find out an ideal generated by S, that is the intersection of all ideals containing S, then it will be the ideal generated by S. Okay, so in this way you can define ideals using a subset of ring. Okay, so here I should stop.